Hi, and welcome to the next lecture unit in the third chapter, which is on the design of codebooks for multi-class to binary reduction schemes and error correcting output codes. So here in this lecture unit, I want to describe how we can define an optimality criterion, so to speak, for codebooks which produce the least amount of errors if we apply them for these multi-class to binary reduction schemes in machine learning. So we have already seen how we can write down schemes like 1 versus rest and 1 versus 1 compactly by these so-called codebooks. And these codebooks defined in their columns how our binary subproblems are defined. So which original classes are encoded as positive and as negative, or which are omitted in this binary subproblem for this column here. And on all of these binary subproblems in the columns, I now trained my binary classification algorithm to produce a model. I will now also give a name to what happens here in the rows, and that what happens here in the rows I will call a code word for class K, because if I use for a certain new X my ensemble here to produce a bunch of predictions, this pattern here is what I ideally would like to produce for an observation from class 1, and this pattern here is what I would like to produce for an observation of class 2, and so on. Now, the major problem comes from the fact that, of course, some of these classifiers will make some mistakes, right, on some observations. So in many, many cases, I can actually not assume that I will produce exactly a matching code word during prediction for any of these rows. So some of these code words that I will produce on some test observation X will not occur at all in my codebook, and now I have to do something about this, and from this we can also then kind of ask ourselves what can we kind of do in the optimal case, and how to create optimal codebooks. So how would we in general now decide which original class to predict from arbitrary code words? So as I said, when a new sample X is going to be classified, we run all of our binary classifiers on that X, we produce, I don't know, maybe scores or probabilities, or maybe direct hard labels. If it's scores, we transform them by thresholding into +1, -1 labels. So for a certain X, we will now create a certain output code word here, and we now have to compare this code word against all of the available code words contained in our codebook. And it seems to be quite intuitive. In order for us to pick one of these original classes, what we should do is we should compute the distance between this predicted code word and the available code words. And we can do this either by Hamming distance, so that would count the number of components that are different between two given code words, or we can simply compute the L1 distance between code words. So this is nearly the same thing. The only difference is if we compute the Hamming distance, if there's different components here, it's always a distance of 1. If we compute the L1 distance and we have a +1 and a -1, that would be a distance of 2. But if we have a 0 and a 1, or a 0 and a -1, that would only be a distance of 1. So producing a completely wrong label produces a penalty of 2 points, but producing a wrong label for an omitted class in this encoded binary subproblem only produces a penalty of 1. Now here's an example. So for example, maybe I'm producing this code word here, which is exactly, I guess, also this guy that I put into this example here. I can now easily compute the L1 distance. So I can, for example, compute the distance from this guy to this guy. So that would be 3, because there's a 2 difference here and a 1 difference here. I can compute the distance to this guy here. That's a 2 difference here. That's a that's a 0 difference here, a 0 difference here, and a 2 difference here. So the overall distance to class 2 would be 2. And again, there's a difference of 3 from this guy to this guy. So I would actually pick the second class and predict that, because here L1 code word distance is minimal. Now, does that tell me something of how I could actually maybe define a good code book? Yes. Let's, for example, assume that we're giving a test observation, and this test observation has a true label of 2. And the produced code word pattern during prediction looks like this. And again, now I compute, well, first of all, I can now see that there's an error going on for the second component, right? So the first class was actually predicted, the first classifier actually produced a correct prediction, the third one as well, but the second one produced an error in prediction. Now if I compute again these L1 distances to available code words here in my code book, I get again this pattern here of a distance of 3, a distance of 2, and a distance of 3, and I would pick this second class here as my overall prediction, and this error here that happened in the second component seems to have been effectively corrected. And this motivates a desirable characteristic in such a codebook. I want to be able to have as many of these errors in individual components be corrected as much as possible. And these types of codes or code books that do exactly this are called error correcting output codes. And they are also a very well-known principle in coding systems, for binary digital systems, and in discrete maths. And there's a pretty obvious property that I would like these codebooks to have, and that is called maximal row separation. So pretty obviously, all code words in my codebook should be well separated in Hamming or L1 distance from all of the other code words. The reason being is if code words are very similar, very few component errors can actually result in an overall error. On the other hand, if the minimum distance between any pair of code words is d, I can correct at least d-1 divided by 2, and then the floor of that, single bit errors. Why is that? For example, assume that there is a distance of 5 between all of these code words here, and then I make a mistake in 2 components. Distance will still be minimal to the correct row, to the correct code word. And the same if I have a distance of at least 7 between all of my code words, I can correct errors in 3 components. If I have a distance of 9, I can effectively correct for errors in at least 4 components, and so on. So this maximal row separation is a pretty obvious thing I want to have. Another desirable property, which is maybe a little bit less obvious, is column separation. The reason for this is that my columns should be uncorrelated because these columns encode learning problems, that I run my learning algorithm on, and it's usually the same algorithm that I use for all of the columns. So if these columns effectively encode very, very similar learning problems, my learning algorithm will also make correlated mistakes when it learns these correlated binary subproblems. And my error correcting output coding scheme will only succeed if the errors made in the individual classifiers are relatively uncorrelated, so that the number of simultaneous errors in many classifiers is actually quite small. So I would like to ensure that there's quite a high distance between all of my columns, but also the distance should in this case not be too large, because on the other hand, if columns are completely complementary to each other, they will still be very highly correlated. So this results in this kind of optimality criterion here, where I want to maximize distances between rows as much as I can, and I want to make distances between columns not too small, because then otherwise they could become identical or highly correlated. But I also don't want to make distances too high, because otherwise I create these complementary columns. So distances between columns should be on a medium level. So short remark on this principle. So in general, if there are k classes, there will be at most 2 to the k minus 1 binary columns because of symmetry. And for example, if k equals 3, there are only obviously 8 different possible columns because I have exactly 2 choices for each entry here. Yeah? Of these 8 possible columns, half are exact complements of the other half. And of course, I also don't really need any columns that contain exact ones, contain only ones or only minus ones. And this results now in this overall counting formula here for all potential binary columns. Now let's assume I have a budget to train exactly L binary classifiers and to want to find an error correcting output code with maximal row and best column separation. So if G is approximately 10 or less, or 11 or less, I can still run something like exhaustive search to find a codebook that has very good row and column separation. However, if there's more than 10 classes, this exponential growth of the number of codebooks in G becomes more and more challenging and too prohibitive for me to kind of iterate over all potential codebooks to find the optimal one. And in this original paper by Ditterich et al., they now employ the randomized hill climbing algorithm for this task to still be able to heuristically optimize overall potential codebooks. And I want to at least summarize how that works. So what we do in this randomized hill climbing algorithm is that we create G code words of length L by randomly drawing these. And any pair of such random strings will now be separated approximately by a Hamming distance that is binomially distributed with a mean of L divided by 2. So I'm at least initializing hopefully quite well. And now I'm trying to iteratively improve the code by doing the following. The algorithm now repeatedly finds the pair of rows which are closest together in Hamming distance. So maybe this guy here is in row distance closest to this row. And I will now also find the pair of columns that have the most extreme distance. Either they are too close together or they are too far apart. And I will now look at these intersecting points here of these 2 rows which are too close together and these 2 columns which are either too close together or too far apart. I will now swap out the labels here in this codebook so that column and row separation are improved the most if I'm only allowed to change these 4 positions here. And this procedure, when that procedure at some point reaches a local maximum, I will then have the algorithm choose random pairs of rows and columns and improve their separation. And that gives me a heuristic procedure to hill climb on this property of maximal row and column separation, and hopefully at the end, with a predefined budget of L classifiers, define a well-working, hopefully nearly optimal codebook for the binary reduction scheme.